3.1 talks about maximum and minimum values. So if I think of a path y equals some f of x, and I'm walking left to right. So when I'm looking at some points, if I walk left to right, I have x equal a. Actually, let's go by maximum minimums first. So maximum, if I walk left to right, when I get to this point, when I get to point B, at point B, I notice that if I am standing right there, if I look to my right on a small interval and to my left on a small interval, I am at a peak. I could tell that that's not the highest point. There is a point higher than that. But around where I am, around B, it seems I'm standing on the tip of a small hill, if you might, right? And that's what we call a local, maximum. So what is a local maximum? A local maximum is a maximum around a point, provided you're not looking that far, just barely around it, in the vicinity of that point. So x equal b is a maximum. If I keep on walking, when I get to point C, I notice that at x equals c, I am at the bottom. That is, if I look to my right, I'll be going up. If I look to my left, I'll be going up. That's the definition of a minimum. But since I'm only looking in a small interval, we call that a local minimum. I keep on walking. When I get to point D, I notice that point D are bounded by a small interval. If I look to my right or to my left, if I take one step, I'll be moving down in either direction. We call that a local maximum. Local because I'm not looking far. I could tell there's a point higher than that and another higher, but I'm just looking locally in that specific interval. I walk to the right, I get to point E. I notice at E I am at a minimum. Why is that? Because if I move to the right, I'll be going up. If I move to the left, I'll be going up. That's the definition of a local minimum. Now, when I get to point F, if I look to my right, I'm going up. If I look to my left, I'm coming down. F would be neither. F will not be a maximum nor a minimum. If you say it's a local minimum, then you're saying if you move to the right or to the left, you should be going up. That's not happening. And if you say you are at a local maximum, then if you move a unit to the right or a unit to the left or a bit to the right and a bit to the left around that point, you'll be coming down. That's not happening either. So, local means inside. You notice x equal a and x equal g, I didn't talk about because they're not local. Local means inside. I could put an interval around it. If I look at a, I could put an interval to the right, but I'm not sure what's going on to the left. And if you look at G, I can put an interval to the left, but there's nothing I can do to the right. So those points you leave out of the local. They're not local maximum or minimum. But if I look at A, I notice that's the lowest y value of them all. We say that's the absolute minimum. And when I look at B, or when I look at G, I notice that x equal G, this y value is the highest of them all, so we say that's an absolute maximum. Now, I do want to point out how this works. Anytime you're given a graph, you figure out the locals first. Then you look at the endpoints. Now, an absolute maximum could be a local maximum. That could be. You could have the highest y value. Here's a graph. Here. If I look at this point, call this L. L is a local maximum because around that interval, that is a maximum, and it is the highest y value among any other y value. It's also an absolute maximum. So absolute is simply among all the maximums, what is the highest you could ever have. So, putting that in a table, given that C and f of C is defined in the domain D, f of C is a local minimum if, so f of C is a local minimum if near C, around C, the y value is lower than all the other y values. We call that a local minimum, just around it. We call it a local maximum if around that C, the y value at C is bigger than all the other x values, but again, around it by a small margin. Absolute maximum, the absolute and the absolute minimum of f of C is an absolute minimum if f of C is less than all the other y values in the domain, and we say it's an absolute maximum if the y value is bigger than any of the other y values in the domain. So here's an example, example 1. For each of the numbers a, b, c, d, e, and f, state whether the functions whose graph is given has an extreme value or not. Well, let's see. X equal a. Actually, let's go that route. X equal a, I'll get to at the end. X equal b, we say local minimum. Moving on to x equals c. At c, I am at this point. Do you see that if I move to the right, I'll be going down, and if I move to the left, I'll be going down? That's a local minimum. I'm sorry, going down. It's a local maximum, right? So that's a local maximum because if you move to the right, you'll be going down, to the left, you'll be going down. So x equals c is a local maximum. And if I keep on walking, I get to this point. Well, this point, you're at x equal d. You're not really here, you're here. Do you see if you move to the right, you'll be going up? And if you move to the left, you will be going up? Well, if to the right I move up and to the left I move up, that's the definition of a local minimum. Here's another point. E. Around E by small margin left and right, this is a peak. That is a maximum. Well, now what? Now the endpoints. At x equal a, I can't call that a local because it's an endpoint, and f the same deal. But when I look at those, I say, okay, look at the graph and tell me what's the highest y value. Isn't that the highest y value? So x equal e is not only a local maximum, x equal e is a local maximum and an absolute maximum as well. F is the lowest y value. X equal f is not a local, but it is an absolute minimum. How about x equal a? Well, x equal a, since it's not a local, and it can be an absolute because that's higher than it, that would be neither. Endpoints are either absolute or neither. But locals could be local maximum or minimum, and they could be absolute as well. Now the next example, we're going to set few graphs. Sketch a graph. There are so many answers to these problems. You could do this so many different ways. So sketch me a graph between -1 and 4. Sketch the graph of a function that is continuous and has the given properties. Absolute minimum at 3. 1, 2, 3. Absolute minimum at 3. Let's make sure none of the y values go below that point. Absolute maximum at -1. At -1, let's make sure that none of the y values are higher than that. A local minimum at 0, that's how a local minimum goes. You could go down a bit, you could go up a bit, any of those will do. And a local maximum at 1, a maximum at 1, maximums look like this. So one possible graph there. That's one possible graph. That's the absolute maximum because that's the highest y value. That's the absolute minimum because that's the lowest y value. And we do have a local minimum at 0, a local maximum at 1, and there it is. Again, there are so many different options. This could be shifted up or down. Another one from -1 to 4. Local minimum. We have a local minimum and an absolute maximum. So it doesn't say where, anywhere. A local minimum. Okay. Well, a local minimum and an absolute maximum. So minimum, I could say that's a minimum right there. Absolute maximum, that's easy. Just continue on. So minimum look like this. If I make this just a curve running this way. Now, that'll do it. There. That graph has an absolute maximum and a local minimum right there. It doesn't say anything about anything else. But that's good enough. If I really want it not to have an absolute minimum, you can say that's an absolute minimum. That's not what they want. They didn't say that, but let's say I want to make sure it doesn't have an absolute. So you know what, there. I could run down. Right? And I could not include that point. There you go. That's one possible way of doing it. Or, and that's no longer an absolute. Oh, but this has an absolute. I see. Now it has a local maximum. You're going to say, but that's not what they wanted. A local minimum and absolute maximum. So I could say, yeah, there is no other way of doing this. Okay, how about giving me a graph that has no extreme values? None whatsoever. A function that's always increasing or a function that's always decreasing. That can't have an extreme value if I don't include the endpoints. No local, no maximum, no absolute. Sketch the graph of f and use the graph to find the absolute maximum, absolute minimum. We're just focusing on absolute maximum and minimum in this case. This is an upside down parabola. So if I go to 1, there's the graph. And if I was to say, well, what do we have? sketch the graph we did. What do we have? We have an absolute max at x equals 0. And how about this graph? Well, this is a radical. At 1, I am at 1. And at 4, I am at 2. How about here? Well, this graph has neither. And how about that last graph, the sine wave? The sine wave starts at 0, right? Runs up to 1. Not included and included, right? This is pi over 2. I was going to continue on, but there's nothing there because we just stopped there. Well, we have an absolute minimum at x equals 0. Now I'm gonna stop here and do the rest on another video.